In the field of engineering, there are few projects more challenging and demanding than the design of ships. They are vast floating towns that need to both safely convey thousands of people in comfort while also actively battling one of the most hostile environments in the world, the open ocean. The amount of thought that actually goes into every facet of your average ship's construction, every system, it's mind-boggling when you really think about it. On this channel, we've looked at how ships work before, the various bits and pieces that actually keep them running. From their complex lighting arrangements, to their stories-tall rudder installations that can turn thousands of tons of metal, down to the actual method used to weigh the ships at all. Ladies and gentlemen, I'm your friend Mike Brady from Ocean Liner Designs, and this is how ships work. Picture this. It's sometime in the 1800s, and in a dense rain squall, a big ship is fighting its way through the churning sea. But to the crew's horror, directly ahead, a huge shape materializes out of the mist, the bow of another ship coming right for them. There's a devastating crunch as the two vessels collide, and there can be no hope for rescue. This story must have played out countless times at sea through history, especially off the busy coastlines near the world's trading ports. And while there have been marked sea lanes for centuries, the ocean doesn't really have line markers, stop signs, or stoplights like your local highway. It took some serious thinking and coordination to come up with a system that would stop this exact kind of scenario from happening again and again. You've probably seen red or green lights on the side of a ship, or even on an airplane. But where did these colours come from, and why did we pick green and red? What's all those different lights mean, and how does it actually help ships safely navigate? Today, ships are virtually festooned with lights of all different kinds that do a lot of different jobs. They're part of a very clever system that allows other crews within eyesight to tell a lot about what that ship's doing just from a glance, but the system isn't always fail-safe. Ladies and gentlemen, I'm your friend Mike Brady from Ocean Liner Designs, and today we're going to figure out just what ships' lights really mean. So, to understand why ships have the lights they do, what they mean, and how they can help, we need to take a look at some good old-fashioned history. For a long time now, ships have been equipped with white, red, and green navigation lights. Titanic, the most famous ship of all time, one we've talked about quite a bit, had them as well, of course. She had white mast lights and a white stern light, along with red and green side lights located near the navigation bridge. In James Cameron's Titanic, you can see a great shot of her starboard green navigation light when Captain Smith is inspecting the ship after the collision with the iceberg. And as it turns out, the laws and regulations that mandated these lights were actually in place decades before Titanic was even a thing. Port and starboard are concepts you're probably familiar with. In sailing terms, port refers to the ship's left-hand side, while starboard refers to the other. So the word starboard is thought to have come from Old English, which essentially meant steerboard, where early helmsmen controlled the ship, steered it, with an oar or a paddle from the right-hand side of the vessel. Even after ships got centrally mounted rudders, though, the association stuck. Originally, from the Middle Ages, and right through the Age of Sail, the ship's left-hand side was called the larboard side, from the Middle English for laid side, where the ship would be laden, that is loaded with cargo. Presumably it was done that way so a ship could come alongside a quay without damaging the steering board over on the other side on the right. Now, there was a big problem here though, because in a roaring gale, or the heat of battle, you can imagine that starboard and larboard might just sound the same. So eventually larboard became known as port, and it hasn't changed since. At least, that's what we theorize anyway. In the old days, when ships still had four castles and fighting tops that made them look more like Teutonic castles, it would have been very difficult to keep fleets of fighting ships together at night without breaking formation, getting scattered over miles, or bumbling into each other. Inevitably, the solution came in the form of lamps, burning oil or tallow, which could be hitched to the ship's yards or her stern and be seen by friends nearby. That, at least, let others know there was a ship there, but what direction it was going in, and what exactly it was doing at all, remained, to observers far away, a complete mystery. Something obviously needed to be done about this. Through the 17th and the 18th centuries, ships still rigged lanterns at night if they wanted to be seen, but confusion could still abound. Lights, spotted far off into the distance, could suddenly turn out to not be far off in the distance at all, but mounted to a smaller sailing ship you and your vessel is about to smash straight into. In 1836, the Royal Navy had had enough. They decided to put some simple rules in place that the rest of the fleet could observe. They decided that ships needed to mark both sides independently with a color-coded system. Red and green were chosen for this, and honestly I don't really know why, but we can make a few guesses. For one, red and green are on opposite ends of the visible colour spectrum, and very likely not to be confused for one another. That is, of course, you are red-green colourblind. Of course, there are very few things on Earth that naturally glow green or crimson red, and both colours do really well at preserving our night vision. But whatever the reason, the very simple system worked, and it stuck. The Navy had great success, and soon all British ships, including merchant vessels, were built and fitted with red and green lights. The success of the system is down to its simplicity and a few key design choices. If you were sailing in the dark and saw this, red on the left, green on the right, then you could make the assumption that a ship was coming right at you. If, from directly ahead, you only saw green, then that would mean that there was a ship off in the distance heading across your bows from left to right. If you saw only red, then the opposite was true. So to make sure the port and starboard lights could only be seen from specific directions like this, they were fitted with screens that basically prevented the light from being cast where it shouldn't and confusing the image. But there was still a problem. If you looked into the darkness and saw this, a green light, then you'd know, as we said, the ship would be heading left to right. But without more visual clues, you'd be in for a surprise, because if we lighten things up a bit, you'd see that the ship is actually kind of on a collision course with you, so more needed to be done. Mast headlights did a huge deal of good when they were added into the mix. By putting another light, a simple white light, high up in the mast, then the direction of travel could be more easily ascertained, and a glance at the other ship's direction might provide some guidance on what was really going on off into the darkness. So with a precedent set for requiring navigation lights aboard ships, other nations soon followed suit. In 1846, the UK published the Steam Navigation Act. This enabled the Lord High Admiral to publish regulations stating that all seagoing steam vessels had to be equipped with lights. The Admiralty exercised its powers in 1848, requiring steam vessels to display green and red side lights, as well as a white masthead light while sailing, and a single white light when anchored. The rest, as they say, is history. With navigation lights mandated and a system now internationally recognised, safety at sea was vastly improved. See, in Titanic's day, ships were fitted with red and green and masthead lights, but they were also provided with a stern light. That way, even more information could be communicated to any other vessels nearby. Since red and green navigation lights could not be seen from astern or behind, the presence of a single low light could mean only that a small vessel was stopped in an anchor, or that a bigger ship was steaming away from you. As with all things, the system wasn't perfect, and there was still room for improvement. The world's oceans had long been split into vast sea lanes, just like a highway, but the rules that governed how ships should respond to one another needed some tweaking. You know that thing that happens where two people walk towards each other on the pavement or the sidewalk, and they both start trying to dodge each other in the same direction? We've all done it. On the sidewalk, it's uncomfortable, but funny. At sea, it can be deadly. In 1972, there came a revolution with COLREGs, the international regulations for preventing collision at sea, which stand as the rules of the road to this day. Naturally, the usage of lights plays a huge role in this set of 41 rules. In fact, the first few sets of rules cover definitions, sailing, safe speeds, and collision avoidance. We'll come back to that. But rules 22 through 30 specifically focus on lights on ships of all sizes and exactly how they need to be displayed. It's that important. For example, Rule 22 on the visibility of lights makes it all quite clear that ships of certain lengths need to have their masthead, stern, and side lights visible out to a number of miles. Rule 23 talks about powered vessels like cruise and motor ships down to powerboats, that they need to display a forward-facing masthead light, a second masthead light higher up and further back, the red and green side lights, and a stern light. Rule 21 gets even more granular. It tells us exactly how the lights need to be displayed. Remember I mentioned Titanic, that her lights had those screens to make sure the light could only be seen from ahead and to the side? Well, COLREGs goes into specifics on that exact point. Masthead lights need to be visible from dead ahead to 22.5 degrees to either side, and only that much. How about the red and green side lights? Well, the same, but with 112.5 degrees of arc over the horizon. It's a brilliant, simple system that virtually all floating registered vessels have to follow. So, armed with all that information, and with ships lit up nice and bright at night time, just how do ship captains use the lights to avoid collision? Well, looking out and seeing a ship's lights can tell the vessel's master an awful lot about what's going on out there, but of course radar and modern-day communication systems are vastly more important for figuring out which ship is moving which way and why. The biggest ships, I'm talking about your immense couple of 100,000-ton bulk carriers and tankers. They can take literal miles to stop. So ships' captains have to be thinking quite a few steps ahead. If there is any miscommunication or confusion, well, there's just nothing that can be done. Disaster will play out in slow motion. For example, take the Admiral Nakhimov. She was a Soviet cruise ship that we covered on this channel a few months ago. She'd just departed on a pleasure cruise on a brilliantly clear night. Ahead and off to her starboard side were spotted the side and mainmast lights of a tanker, clearly bearing down on them but miles away. Now, radio communication was established and all should have been fine, but the tanker still slammed straight into the side of Nakhimov and sent her to the bottom in just a few minutes, killing hundreds. Remember that thing I was talking about when people try to dodge each other on the sidewalk? Yeah. So there obviously needs to be a simple set of rules in place to prevent exactly this kind of thing from happening. And COLREGs authors were faced with the challenge of keeping things as simple as possible so that what applies to a 20-foot powerboat could apply to the 150,000-ton Queen Mary too. COLREGs gives a simple solution. If two ships spot one another's masthead and side lights from ahead in clear conditions at nighttime, they both need to adjust their courses to the right, to starboard, so that they pass port to port, that is, red light to red light. But in many ways, a head-on approach like this is actually quite a simple situation to deal with. Where it can become most confusing is converging courses, where one ship is trying to cut across the path of another. Now, this is the kind of situation the Admiral Nakhimov found herself in, and COLREGs handles it quite simply. The two ships involved in that kind of situation are instantly given specific roles. The first, the ship that has the other vessel on its starboard or right-hand side, and can therefore see the other ship's red port navigating light looking back at them, becomes the give-way vessel. The other ship, which can see the give-way vessel's green starboard navigation light off on their left, is designated as the stand-on vessel. Now, the rules call for both ships to act as predictably as possible. The stand-on vessel is given a kind of right-of-way, so to begin with, it maintains speed and course, unless the skipper judges that the give-way vessel isn't giving way. Now, in return, the give-way vessel should slow down or alter course, or both, by veering slowly over to starboard to the right-hand side and letting the stand-on ship ahead. But if it becomes clear that the give-way vessel isn't giving way, then the stand-on vessel has to take avoiding action, either slowing or turning off to starboard, but not to port unless absolutely necessary. Therefore, just veering away from the other ship. In general, turns to port or off to the left are discouraged in these scenarios because they can create confusion and they actually heighten the risk of collision. In low visibility though, things change completely. Simply put, COLREGs Rule 19 says there are no give-way in stand-to vessels. Each ship has to take avoiding maneuvers by slowing well down and veering off to starboard, making full use of radar, lights, signals, and horns. So, in a nutshell, that's why ships have red and green lights. It's part of a brilliant, simple system that's been refined since the early 1800s. It's a kind of language that all ship and boat skippers speak and hopefully know virtually by heart. But the truth is though, even with lights, nighttime navigation is really difficult. Without radar, it's hard to know exactly what it is that you're seeing, but the lights and rules attached to them can give crew and their skippers some crucial clues. In fact, there's a whole slew of other light combinations that can be displayed to give even more information. For example, a ship that's run aground and stopped should run lights that look like this. Or a big ship that's not under command but is still underway, so for example, a big tanker whose rudder is locked up that can't stop, well, they need to be lit up like this, nice and red, so that everybody else knows to stay very far away. So to sum it all up, I'll leave you with this little poem from all the way back in 1867 that perfectly runs through the give-way regulations that have remained little changed ever since. It goes like this. When both lights you see ahead, starboard turn, and show your red. Green to green, or red to red, perfect safety, go ahead. If to starboard red appears, it's your duty to keep clear, to act as judgment says is proper, to port or starboard, back or stop her. But when upon your port side is seen a vessel's starboard light of green, there's not so much for you to do, for green to port keeps clear of you. It's the middle of the night. A steamship is tearing through the darkness at full speed, but suddenly something dangerous is spotted up ahead off to the ship's right hand or starboard side. With only seconds to act, the desperate officer of the watch roars out a simple command: hard to starboard. and the helmsman at the ship's wheel begins urgently spinning the big wheel over to the left. But, hang on a minute, you might ask. The officer saw the obstacle is off to the right. Why is he calling out to seemingly steer into it by ordering hard to starboard? And then, to confuse matters further, why did the helmsman turn the wheel to port or over to the left? This is all to do with an archaic system of commands which is at the very heart of the story of how ships steer, and how they've operated through the centuries. It's actually a really fascinating story. How ships have been able to move themselves and maneuver well as they've increased exponentially in size is really remarkable stuff. Today, we'll take a look at the history, how, through 3 distinct ages, ships have handled themselves differently, all the way up to today, and the high-tech systems that make sure even the most monstrous of floating vessels can turn at all. We'll come back to our example from the start of the video soon, but first we need to cast our mind's eye way back to the dawn of ocean-going exploration. In our earliest days, boats were very simple things, and they were naturally rather small. It didn't take a whole lot to turn them. That, and we were constrained only to calm waters like lakes and rivers, which are quite shallow and calm. Ancient Egyptian carvings and illustrations show boats being propelled with oars, and mounted at the after end or the stern of the boat is an oar meant purely for steering. More advanced Egyptian vessels from around the Middle Kingdom featured a pair of the things, with dedicated operators turning them left or right, guiding the vessel as it moved through the water. Now, the concept is fairly simple. By altering the direction of the steering oar, you're essentially creating drag on one side of the boat, meaning it will turn towards that direction because the flow or the momentum is being interrupted on just that side, thanks to the drag. Now, steering oars are really as simple as it gets. They were used on ancient boats on everything from Greek triremes to Roman warships, usually mounted off to one side. But vessels like Viking longboats introduced an addition to the oar. Essentially, a handle that could be mounted horizontally across the width of the ship connected directly to the oar, something even simpler for an operator to use. By turning the handle left or right, the steering oar at the end of it would respond. Now, this simple little handle would become the basis for a system that would be in use all the way until today. It was called the tiller. By the dawn of the Age of Sail, that steering oar had been moved to the ship's centerline and placed at the back, given the name rudder from the Old English word rodda, meaning paddle or oar, and my apologies to Simon Roper for butchering that pronunciation. But anyway, ships now had rudders, and the way to control them was fairly straightforward, and it would remain unchanged for a long time yet. In essence, the rudder was still connected to a tiller, but now ships had become so big that you couldn't just put a crewman with his hands at the tiller to control the direction of movement. For one, you need a score of people to handle the thing. In rough weather, the pressure of waves acting against the broad surface of the rudder would throw the tiller this way and that, presenting a clear and obvious danger to anybody unfortunate enough to be standing nearby. Yeah, ouch. The first approach to this issue was the introduction of the whipstaff. It was really just a long pole connected to the tiller at the back, a couple of decks below, and secured into place with the tough iron fitting called a gooseneck, which allowed swiveling in place and constrained its movements. So acting as a very simple kind of lever, the whipstaff would put the tiller left or right and therefore move the rudder, turning the ship. It was simple but needed a mighty strong helmsman to operate because besides the natural load lessening nature of levers, the tiller needed brute strength to swivel. Still, the whipstaff stayed in service for a surprisingly long time, right up until the 18th century, and it was the control mechanism of choice for ships like the East India Dutchman, Spanish galleons, and British Elizabethan warships. It wasn't until the early 1700s that wheels would be added into the mix. The introduction of the ship's wheel, or helm, named from the Old English noun to helve something, that is to handle a tool or a weapon, absolutely changed the game. Now, wheels could drive the tiller and introduce a kind of gearing. It still needed a lot of strength, but because the wheel was connected through ropes and pulleys, often to a second drum or axle below which actually pulled on the tiller, it meant that the system needed less brute force to operate. Often, on sailing ships preserved today, you'll see the ship's wheel seemingly pointed backwards, and many people actually pose for photographs standing the wrong way. It's not facing backwards, it's just positioned that way so that two people can stand either side of it to take up the force of actually turning the thing in rough weather. Of course, by 1700 and beyond, ships were becoming bigger and bigger, but the helm and tiller arrangement stayed in operation for a very long time indeed, and virtually unchanged at that. The thing is, the wheel, connected with ropes and pulleys, needed to be positioned directly above the tiller, and it could still be a dangerous job. In heavy seas or a storm, the wheel could get away from the helmsman and spin freely at extreme speed. It was known to kill. In fact, a crewman aboard the SS Great Eastern was killed in the latter 1800s because the ship's wheel backspun out of control and clipped him. Ships' wheels became bigger and bigger because, not unlike the wheels on a penny farthing or the gears of a bicycle, a bigger wheel requires less movement to turn the tiller further. It was a clever, simple system which remained unchanged until the days of steam. And even then, things only changed slightly with the introduction of machinery designed to lessen the workload on the crew. By Titanic's day, believe it or not, ships still used tillers, but the mechanics involved and the sheer scale of the machinery is astounding. Titanic's rudder alone stood the height of a 7-story building and weighed over 100 tons. Not only that, but the ship that rudder needed to turn weighed itself over 50,000 tons. Now obviously, human brute force just wasn't going to cut it. Fortunately, there'd been some pretty serious mechanical inventions that helped a lot. Instead of human power turning the rudder, Titanic and other steamships just like her had her tiller connected to a set of steam engines. Now these were basically miniature versions of the kind you'd expect to see actually powering the ship down in the engine rooms. They sat inside a special compartment directly above the rudder in the same way the ship's wheel had once been positioned back in the days of sail. The steering engines were geared directly to a huge quadrant-like tiller, which was attached directly to the rudder's stock, or its central axis. Running the engines, fed of course by high-pressure steam, in one direction would turn the gears, the tiller, and therefore the rudder below. But the ship's main wheel couldn't be mounted that far back at the stern. Ships by that point were nearing 1,000 feet in length, and the bridge was well far forward. So instead, a machine called a telemotor was devised which controlled the steam engines that were so far away. The telemotor was an early type of servo motor, and it employed a cylinder in the wheelhouse and a matching cylinder all the way back at the steering engine. Connecting them were hydraulic lines with fluid, about 70% water and 30% glycerin, to prevent freezing. Turning the ship's wheel would push the cylinder at the wheel, on the bridge, over, forcing liquid through the pressurized pipes and pushing the corresponding cylinder at the other end of the ship, which was connected to the steering engine. Now, springs inside the telemotor cylinder would give feedback to the helmsman, meaning that as the turn became tighter, it would just require more force to turn the ship's wheel. If the helmsman released the wheel, the springs would return the ship's wheel to a neutral position, and the cylinders would return to amidships. Now, all of this would engage the ship's steering engines, so that turning the wheel would activate the engines, turning the quadrant, and then the tiller. Now, because of this brilliant system, one man could turn a 100-ton rudder with relative ease. So, let's for a minute go back to our example at the start of this video. When Titanic approached the iceberg, First Officer William Murdoch ordered hard to starboard, which would make it sound like he was ordering a turn to the right into the iceberg. But the archaic way of calling out steering orders from the time meant that Murdoch was ordering the helmsman at the wheel to put Titanic's tiller to starboard on the right-hand side. Now, this would, of course, turn the ship's rudder in the opposite direction, to the left. By ordering the tiller hard over to starboard, Murdoch was actually ordering an emergency turn to port. So the helmsman turned the wheel to the left as fast as he could. The telemotor drove the steering engines at speed, and they jammed the quadrant tiller to the right, to starboard. Titanic's massive 100-plus ton rudder swung to the left, but of course, it was too late. This system became the norm for all big passenger and warships. In fact, those destined for use in combat made use of a series of emergency steering positions deep within the hull. For example, Lusitania, which had been secretly designed as a merchant cruiser and might end up in a gun battle, had a special steering position in the steering engine room itself, very near to the waterline. Emergency steering compartments were extremely important, so that if the bridge was hit and the main wheel was destroyed, there was at least one other position where the ship could be controlled. And since the wheel there was geared directly to the steering engines themselves, there would be no need to worry about hydraulic pressure or any of the lines getting hit. Now, you might be surprised to know that many big ships today still use tillers. Even if the ship has more than one rudder, a pair of tillers can be connected to something called a tie rod, which turns them both together in the same direction. Today, steering gears are mostly hydraulic, relying on pressurized oil lines and motorized pumps to respond to helm commands and push cylinders either side of the tiller, thus turning the rudder. Telemotors are still in use, but the signals they transfer back to the steering gear can be hydraulic or electric. The telemotor typically communicates with a receiver, which engages the hydraulic system and turns the tiller whichever way it needs to go. Modern control systems are split into specific sections. For one, the bridge control equipment, including the actual machinery needed to receive instructions from the bridge, like transmitters, hydraulic lines, and so on. Then there's the power unit, the main source of power to the rudder itself, like the pumps, the electric motors, and so on. Finally, the transmission unit, converting the signals from the bridge into actual mechanical movement of the rudder. Today, working in among the whole system is something called the hunting gear, a system devised to arrest the rudder's movement once the required change in direction or angle has been achieved. It effectively communicates the position of the rudder to the pump control and prevents over-positioning of the rudder, keeping it in position until the next input is made. The system is today actually quite complex and relies on a host of control rods, floating levers, power units, and more, so please excuse this rather rudimentary explanation, but the point is that rudder-tiller telemotor system has been perfected very well indeed. Now, there are a few more systems used by ships today. Two of the most impressive use screws or propellers. Bow thrusters became a must-have for all big ships when they were first introduced in the 50s and 60s. This clever system relied on one or more impellers, basically propellers mounted sideways, inside the bow with ports that could allow the bladed impeller to turn either direction, thus providing thrust to the ship's bow. Today, most, if not all, big cruise ships use bow thrusters, and they're crucial in docking and maneuvering in tight spaces. Being able to swing your bow around under your own power without the use of tugs is a huge deal and makes actually moving ships in excess of 100,000 tons or more significantly easier. Because back in the old days, the ship's bow could swing wildly away with no way to arrest it without having like half a dozen tugs or more on standby. Probably the most revolutionary step forward in maneuvering ships has been the Azipod, which does away with tillers and rudders entirely. This clever system uses massive pods slung below the ship's stern. They serve two purposes, mainly acting as the ship's main propulsion system. Pointing directly ahead, the thrust will drive the ship along like usual, but the pods can swivel in place, and even a slight change in their direction will alter the ship's course in the same way that a rudder would. They're powered by diesel generators from above, which produce monumental amounts of electricity to power motors inside. Those fitted to the Queen Mary 2, for example, can rotate a full 360 degrees thanks to hydraulic steering motors mounted above, but each pod weighs as much as a Boeing 747 jumbo jet, and the motors inside have an incredible 21.5 megawatt output. That's a lot of raw power potential. So that's how it's done. Incredibly, aside from the introduction of hydraulics and pumps, things like that, and Azipods, the rudder-tiller system is strikingly similar today to what preceded it way back in the 1300s with the whipstaff. The principles are still largely the same. What has absolutely changed is the sheer size of ships. It really boggles my mind when I see just how enormous these things are. For example, the upcoming Disney Adventure, which was just floated out, has a hull of about 208,000 gross tons, which is enough space for over 8,100 people. To turn, she'll need 3 Azipod thrusters. What an absolute monster of a thing. You can't quite imagine one poor bloke at the back absolutely straining on a steering oar to turn it, so it's a good thing that technology's got us to where we are today. I have a fun fact for you. Back in 1936, the Queen Mary, one of history's most famous ships, was introduced as the biggest in the world with a displacement and a tonnage both around 80,000. But the Queen Mary 2, the modern day equivalent, has a very similar displacement, around 80,000 tons, but it's almost twice as big at 149,215 gross tons. So although the two ships weigh essentially the same, Queen Mary 2 is much bigger. Now, wait a minute, I hear you ask. What does all this actually mean? Well, to get to the bottom of it, we need to know how to weigh a ship. Let me explain. In general day-to-day life, the concept of weighing something is pretty simple. We just whack something on the scales to see how much it weighs. But how on earth do you weigh something as large as a ship? You could set up some kind of scales in a dry dock, but the truth is even the smallest of boats are nearly much too big to fit on any sort of scales, and that's also the fact they spend most of their lives in the water. Just how could you weigh something that weighs nearly as much as 1 million people stacked on top of each other? Well, thankfully, some clever brains have figured it all out. Today we'll learn the difference between ships' weight, tonnage, and displacement. Then we'll see just how these massive vessels are actually weighed and how their weight can be impacted by some surprising factors. If you've watched a lot of this channel before, then you probably know all about Olympic and Titanic. But if you're new to all this, then I'm sure you've at least heard of the latter ship. Let me give you a quick rundown. These two sister ships were built by the same yard using the same materials, mostly steel, but Olympic came in at 45,324 gross registered tons, while Titanic measured in at over 46,000. Now this, of course, made Titanic the biggest ship in the world, but it may surprise you to learn that both ships were of essentially identical proportions in size, like length and width, and Titanic had very little added machinery that would tip her over the scales. This is because that little figure I mentioned, gross registered tons, is actually an archaic measure, not of weight, but of a ship's internal usable volume, all the combined usable space inside. Knowing the difference between all these confusing terms like net tonnage, gross tonnage, displacement, and so on, it's a really great way to start before we learn how to actually weigh a ship. So let's begin with probably the most simple metric, displacement. Displacement is commonly used in relation with the mass of a given ship, although surprisingly it's not actually a measurement of the ship's own weight, it's the amount of water mass that's displaced when a ship is floating freely on a body of water like the ocean. We know thanks to Archimedes that the amount of water displaced by a ship is equal to the mass of the actual ship itself. It's a raw, basic measure of a ship's sheer size and mass, but it can be read a few different ways. First of all, there's light displacement. Light displacement is the mass of a ship that is completely empty. That means no cargo, the fuel tanks are empty, empty ballast tanks, no consumables like food, and totally void of any passengers and crew. Truly a completely empty vessel, just a big mass of steel. And of course, a ship is rarely, if ever, in this state, but it gives naval architects a good basis upon which to gauge the performance and the stability of the hull during design. This is usually calculated during the design stage, based upon measures of the hull volume and the actual materials being used, and then it's checked when the ship is finished. Next, there's load displacement. This is a measurement of the ship's total mass while it's floating in salt water up to her summer load line. The water itself is another variable here. Different seasons and conditions can actually impact the salinity, the saltiness of the water, and the properties that the ship finds itself in. It sounds crazy, but put simply, some water is actually just harder to float in. It's why ships have this mark, the Plimsoll mark, painted on their sides with different letters for all the different conditions the ship is reasonably expected to encounter. Tropical freshwater provides, in essence, the least buoyancy, the least amount of floatability for a ship, and it will sit lower in the water, while winter in the North Atlantic will see the ship riding higher because of the salty, dense seawater. The Plimsoll mark is an easy way of making sure from the outside that the ship isn't overloaded for the conditions it's expected to encounter. For example, the summer load line is an indicator of the ship's maximum depth to which it can be filled safely with cargo and passengers and fuel during the summer months. So with a ship full of passengers and the normal stuff you'd expect a ship to be carrying, load displacement gives you a good read on what a ship would essentially weigh during many of its day-to-day operations. Today, big carriers use DWCC, or deadweight cargo capacity, as a measure of just how much cargo a ship can reasonably carry in all different weather conditions. In summer, when the ocean water is denser, ships can actually carry more cargo before they hit their load line, purely because the water is more floaty. Finally, there's present displacement. Now this is the sum of the light displacement and everything that's currently on board at a specific moment in time, and not in the hypothetical. So simply put, it's the mass of a ship at a very specific time in its voyage. It includes cargo, fuel, crew, supplies, and passengers, just like load displacement, but this can fluctuate because food is eaten, fuel is burned, and passengers get on and off. So the same cruise ship on day 1 of its trip will displace way less on day 5 of the holiday when all of its passengers have got off and all the food and fuel have been burnt up. Ships are constantly fluctuating in their sheer mass thanks to the fact they're so big and they support so much life on board. Displacement gives a good, rough indicator of how big a ship is. Historically speaking, it was important for charters and treaties like the Washington Naval Treaty, which sought to limit the size and number of warships being built around the world. It meant no cruisers bigger than 10,000 tons displacement could be built, but in the end a few signatories ignored this and started building bigger ships anyway. They knew they were well outside those restrictions, but of course they happily reported their ships to be well under the limit. That's a story for another day. So going back to the original example, Olympic and Titanic, both ships had a very similar load displacement. They were made out of the same stuff, they were the same size, and after all they carried a very similar amount of people. But Titanic's gross registered tonnage was bigger by about 1,000 tons. Now this is where it can get understandably confusing because tons are usually a measure of weight, right? You know, like imperial or metric tons. But the tons in this context are not that at all. They actually refer, well, originally at least, to barrels of wine. This sounds crazy, but bear with me. Measuring tonnage has a long and interesting history, or I think it is at least. In the most general of terms, tonnage is a measurement of a ship's size. It can be expressed in terms of weight, but usually in terms of volume. The term has been around for hundreds of years, but it's not always represented the same value. The general consensus from historians is that the word originated from the word ton, spelt T-U-N, which was a medieval term for a cask of wine. So the earliest method of measuring ships, their size, was to simply count the number of casks or tons of wine which could be stuffed into the holds of a vessel. That number would be listed as the ship's internal carrying capacity, and it gave a pretty useful measurement of its actual usable, practical size. When ships were charged dues like tax, imports, and things like that, it would then be based on this measurement. See, you can make a ship out of insanely heavy material. It'll displace 100,000 tons because it weighs so much, but in theory it could be so small inside that only a tiny portion of it can actually be used for anything. And its tonnage, that is the usable interior volume, could be something silly like 100 tons. Tonnage gives a more accurate picture of just how much internal space can actually be used and how big the ship truly is. Back in the 15th and 16th centuries, when tonnage was kind of being standardized, ships, like all things, were regulated by their governments, and under the first recorded act in dealing with ship measurements, back in 1492, King Henry V decreed that keels that carry coals at Newcastle should be measured and marked. Now, it's not clear from this decree just how those measurements were to be conducted, but what we do know is that right around this time there was a big change. Instead of measuring by volume, ships were being assessed by the weight of the cargo they carried, so a ton, valued at 2,240 pounds, or 1,016 kilograms, became a standard unit of measurement. As shipping became more prominent and governments wanted to make sure ships were paying their proper dues, there were a number of attempts to create a measurement standard to ensure consistent values. One of the earliest examples is known as the Builder's Old Measurement. Now, this was adopted in Britain by an Act of Parliament back in 1773, but it had actually been in use more informally as early as 1650. With this system, a ship's tonnage was based on the length of the vessel and its maximum width, and it was expressed as tons burden. Builder's Old Measurement would remain the standard for decades and decades, right up into the 19th century, when with the advent of steamships, the standard for measuring had to be reassessed. See, sailing ships at the time were essentially just big open hulls with masts on top. There were no watertight compartments or ballast tanks or internal machinery. Their cavernous interiors were just jammed full of grain or sheepskins or whatever was being sailed out. That all changed with the advent of the steamship. These New Age vessels were built completely differently. They had a larger ratio of length to beam. Significant portions of the ship needed to be dedicated to boilers, machinery, coal, and engines. And then there were all the safety features like double bottoms and watertight compartments. This was all space that couldn't be used for cargo. George Mawson of the British Board of Trade devised a new method of determining a more accurate measurement of a ship's size. So a more accurate size measurement would also mean a more accurate indication of the ship's actual earning potential, and then fees could be determined more appropriately. The Mawson system would feature two outputs: gross registered tonnage and net registered tonnage. Gross registered tonnage, expressed as GRT, was a measurement of the total internal capacity of a ship. Now this includes the underdeck volume, the volume of the 'tween spaces on deck, the superstructure, the deck houses, and so on. But it's important to note that the measurement didn't include the safety features like the double bottom, the navigational spaces like stairways, or the ship's kitchens or galleys, and light and air spaces like trunking. It was just a measure of the total, actual, usable space aboard the ship. The sum of the volume measurement was then divided by 100 to get the ship's calculated gross registered tonnage. So Titanic, even though she displaced around 52,310 tons, had a gross registered tonnage of 46,329 gross registered tons. Now this gave her owners and operators a good indicator of just how big the ship actually was, and it's the figure that was used by trade journals and newspapers to compare her against other ships of the time in the contest for size supremacy. But it was a little misleading. Titanic's hull was absolutely full of massive machinery that consumed a huge amount of that impressive volume. Now that's where, internally at least, another figure was important to show just how much of the ship could really be used by the company to generate some profit. Net registered tonnage, or NRT, was a measurement of the capacity available on board for cargo and for passengers, so it didn't include accommodations for the crew, any of the safety features, none of the storage spaces, the water ballast tanks or space for machinery like the ship's engines or propeller shafts. So whereas gross registered tonnage was a measurement of a ship's total volume, the net registered tonnage was a measurement of a ship's space that could really be used to generate profit, whether it be for cargo, more passenger cabins, or public rooms. Titanic's net registered tonnage, once you took out all that crew space and machinery, was reduced to just 21,831 net registered tons. So, now, with that out of the way, we can answer our question, just how and why was Titanic bigger than Olympic if they both weighed kind of almost the same? Well, put simply, Titanic's designers closed off spaces that on Olympic at least were open promenades and deck space that didn't really factor into the ship's registered tonnage. The owners, the White Star Line, converted these spaces, including the entire B-deck promenade, or almost all of it, into usable, profit-generating spaces aboard Titanic. The changes added about 300 tons to Titanic's overall weight, her displacement, so all that extra bulkhead installation, paneling, furniture and the like. But a lot of cabins were put in for first class that added to Titanic's net registered tonnage, so it increased Titanic's NRT as well as her GRT by about 1,000 tons over that of her sister. So even though Titanic and Olympic had almost identical dimensions, Titanic just had more usable space inside, and so therefore she could boast about, technically, being the largest ship in the world. The Mawson system was accepted and put into use in 1849, and it became law under the Merchant Shipping Act of 1854 in Britain. It would remain in place until the International Convention on Tonnage Measurement of Ships came into place in 1969. This convention, with such a catchy name, was adopted by the International Maritime Organization, the IMO, that year. It was meant to introduce a universally recognized tonnage measurement system. See, before then, a few different systems were still being used at the same time. Of course, they all derived from the Mawson system, but there were still considerable differences between them, enough so that it was collectively realized that a new international system had to be put in place. Gross registered tonnage and net registered tonnage became gross tonnage and net tonnage, respectively, although their purpose was obviously similar. Gross tonnage stayed a measure of the overall size of a ship and its internal volume, and net tonnage is still a measurement of the useful capacity of a ship. It's just been standardized on the world stage. Today, both gross tonnage and net tonnage can be used to calculate port dues and fees. But one final measurement to note is that used in the maritime industry, deadweight. A ship's reported deadweight tonnage is crucial because it represents the overall carrying capacity of the ship measured in tons. For ship owners, this information is critical because it determines their vessel's profitability as well as playing a key role in determining some of the ship's fees and port dues. So for example, massive oil tankers like the Seawise Giant. This ship is the biggest tanker ever built, around 0.5 kilometre long, that's over 1,500 feet, and displacing around 82,000 tons empty. But fill her up with oil and it's a different story. The ship could displace an unimaginable 646,000 tons at full load, meaning that once you subtracted that 82,000 tons of actual ship and steel, she was carrying around 564,000 tons of oil, so her deadweight tonnage comes in at 564,000 tons. It's very impressive stuff. So why is knowing the weight of a ship, or at least having a standardized method of recording the weight, so important? Well, as a matter of physics, of course, it's crucial because the stability and the buoyancy have to be adhered to so that a ship can not only just remain upright in water, but minimize listing back and forth and pitching, or even the risk of just straight up sinking. Physics aside, governments, organizations, and ship owners haven't devoted hundreds of years to perfectly weighing a ship just for safety and the physical aspect. The measurement of a ship ties directly to its operational capabilities and its profitability. Tonnage directly impacts how much a ship can carry, and basically just how much money it can earn. It's all important for big businesses to know just how much profit they stand to make or lose. A ship's measured weight also correlates with a few different safety regulations. For example, gross tonnage dictates requirements for safety equipment, the number of crew, and the training level they have to go through to be certified on their role for that specific ship. So for example, satellite emergency positioning beacons, or EPIRBs, and search and rescue transponders, or SARTs, are required for all passenger and cargo ships measuring in excess of 300 gross tons on international voyages. Crew size regulations are set by the IMO as well, and they're determined by gross tonnage, since bigger ships just need a bigger number of highly trained crew. So, now the all-important question, how do you actually weigh a ship? How do they know how much a ship displaces once it's all loaded up? Well, the easiest way is to observe the draft marks. These can be usually found at the bow. They're often at the stern, and they're sometimes amidships on both sides of the hull. These markings are painted directly onto the hull when the ship is built, and they're maintained as a matter of great importance, because like the plimsoll marking and the load line, the draft marks can be used to calculate just how much weight the ship is carrying. If a ship's sitting deeper in the water, then the water will rise to meet one of the higher draft marks. Now, this is a read of how much water the ship's displacing at that exact moment. When it's multiplied by water density, which can today be read with instruments on board, it essentially gives a general figure of the ship's weight. This is the way it's been done for hundreds of years. In essence, to weigh a ship, you first need to know a few things about it. How it was built, the hull volume, the builder's figures around its light displacement, and then how the ship is sitting in the water. All of this will tell you its weight. Ships have got a lot bigger and a lot heavier over the last few hundred years. The Great Eastern, a behemoth of her time in the 1800s, came in at 18,915 gross registered tons and displaced over 32,000 tons. She was heavier and had even more internal hull volume than the impressive later liners like Kaiser Wilhelm der Große, which launched nearly 40 years later and was the first proper four-stacker ocean liner. In the 50s and 60s, different materials began to be used in ship construction that helped reduce their weight without impacting the internal volume of the ship. So aluminium, or aluminum to our American friends, was used in excess aboard ships, up top in the superstructure where the deck houses and passenger spaces weren't expected to come into frequent contact with the ocean. And this helped save a heap of weight, but it also had some serious drawbacks, probably most dramatically demonstrated when the Italian liner Michelangelo copped a monster wave over the bow, which caved the lightweight superstructure in, killing 3 and injuring more than 50. Today, big ships like the Queen Mary II are built using almost entirely steel, but thanks to welding construction over riveted construction, the ship's actual weight can be kept way down. Factor in that ships now use space-saving diesel engines, and they don't have to have a third of their hull space dedicated to massive boilers and steam turbines, and you end up with a bigger ship that weighs less, but has more inside space. So that's why Queen Mary from 1936 weighs about the same as the Queen Mary II today, but Queen Mary II has almost double the internal space that passengers and crew can actually use. And that is how you weigh a ship. Ladies and gentlemen, it's your friend Mike Brady from Ocean Liner Designs. Thank you so much for watching this video. If you enjoyed it, please leave a comment below. And don't forget to subscribe to the channel because we get new videos out weekly. If you want to support my work and get really cool perks like behind the scenes and early access, please visit my Patreon in the link in the description below, or sign up as a YouTube member. Come and join the crew. As always, stay safe, stay happy, and I'll see you again next time.